Philipp Schlicht from Munster. I thought you were from Bonn, but
That's correct.
who will talk.
Okay, thank you very much, Adrian. First, I would like to thank the organizing committee and the program committee for this great conference. I think it's. Is it on? Can you hear me?
Yeah, no, it's on, just quiet.
Okay. So as I mentioned, the perfect set theorem for analytic sets in ZFC. So I guess the point of my talk is that this may completely fail if you replace the Baire space omega to the omega by kappa to the kappa. So this is the first idea. So there are two topics: perfect sets and superperfect sets. The second topic is joint work with Philipp Lücke and Luca Motoros. And I've given variations of this talk before, so I apologize to people who've heard that before. What's the basic question? I will first talk about perfect sets and then superperfect sets. So we want to replace the Baire space now by kappa to the kappa. So kappa is some uncountable cardinal. So the basic question people ask about which dichotomy is generalized, for example, the perfect set property, which in ZFC holds for analytic sets. The Hurewicz dichotomy, which is the analog for superperfect sets. Superperfect sets given by a superperfect tree, and it's a tree which is kappa branching. So it's so every node there are cofinally many nodes in the tree which have kappa many direct successors. That's a superperfect tree in the context of kappa. And then a related question is regularity properties. For example, measurability associated to a tree forcing. And there are various ways to define this, which we'll see. And so for the context, we always assume kappa is satisfies kappa 2 less than kappa is kappa to be in analogy with omega. And the generalized Baire space is just a sequence of functions from kappa to kappa where a basic open set is given by information of size less than kappa. And then the closed subset of the space are given by trees. Okay, and then so if you collapse an inaccessible, then for the Baire space, first of all in ZFC, every analytic set has the perfect set property. If you collapse an inaccessible to omega 1, then all definable sets, all sets definable from omega sequence of ordinals have the perfect set property by Solovay. And for example, one question is this true when you now replace omega by some larger kappa? And there's an obstacle to this proof. That I'll explain in a second. So what are the definitions I said? So super closed. So what's the analog to a perfect tree or perfect set? So we want the tree to be closed under ascending sequences. So we look at trees where you have a sequence of nodes in the tree, then and then the union of those nodes is again in the tree. And we want the trees to be perfect. So above every node there's a node that has at least two direct successors. So let's say. Let's call this a superclosed tree if it's closed under ascending sequences. Okay. So basically, superclosed tree is the analog to tree in this context, or one analog, obviously. And then, if nu is any cardinal, we look at nu splitting trees. It means that a node is nu splitting if its direct successors there are at least nu many. And we'd say trees nu perfect if it's super closed and they're they're cofinally in the tree. There are cofinal many nodes that are nu splitting. So if you look at for nu equals 2, these are just the perfect trees, and for nu equals kappa, these are let's call them super perfect trees or kappa Miller trees. So this is the tree we look at. So it means above every node there is a node which has at least kappa many direct successors. Okay. So then, if you want to generalize the perfect set property, so this is the obstacle really. So if you just look at Solovay's proof, it doesn't go through because the forcings don't factor properly. So you can, for example, if you add a subset to omega 1, a cone subset to omega 1, and you shoot a club through it, then that two-step iteration is again just adds a cone subset to omega 1. but the second factor is very bad. It destroys stationary sets. So this means that there are lots of different. If you're looking at, for example, you go to an extension with this forcing, and you look at inside. You look at some cone subsets of omega 1 over the ground model. There are many different quotient forcings that could appear. So this is a difficulty in this context, and I would like to sketch how to overcome this in this proof. With this proof, so let's say the perfect set property means that let's call this PSP. Kappa says if we have any subset of kappa to the kappa that's definable from a kappa sequence of ordinals, then this has the perfect set property, meaning it's the set either has size at most kappa, or kappa has a perfect subset, and the perfect subset is given by a perfect tree. Okay, and then analogous to omega, actually, when you collapse an inaccessible, then this perfect set property holds. And I would like to sketch the argument also. But first, some remarks about this. So there's this very important notion of regularity property associated to a tree forcing. So if you have any tree forcing like Sachs forcing, Miller forcing, and so on, there's a canonical way to associate a regularity property to it. For example, in work by Daisuke Kikami, this was done. And then Yuri Komsky and others generalized this to the setting of kappa. I mean, the definitions generalize in a straightforward way. And so what is the relationship with this? So there's a difference because when you consider the forcings, you always consider, for example, we want to look at the analog of Sachs forcing for omega 1 or for kappa. Then the conditions of the forcing are not just perfect trees, but you put the extra condition that the set of splitting nodes in the tree T is closed. So if you have a sequence of increasing splitting nodes in the tree in the forcing, the union of that, you have a union node on top of that. This should also be a splitting node. So I think this was first done in a paper by Kanamori for Sachs forcing quite long ago. For forcing, this is the right notion. But these are different trees, so you get different regularity properties and different something different. And in this case, I just want to remark that if you look at for example, the analog to the perfect set property, this is easily false. So we have to be very careful in this context. Okay. So there are two ways to define the analog to a perfect tree. So one is the type of tree that I defined, and the other one comes from the forcing, and they're completely different results. Okay. So now, then it follows from this that if we look at the kappa-Chang model, which is the least model of ZF, which contains all kappa sequences of ordinals, then in this extension, you collapse an inaccessible to kappa plus, and then every subset in the extension, all the subsets of kappa to the kappa in the Chang model will have the perfect set property. That's a corollary. And another result, let's see. Okay, well, I mean, the perfect subset property can be characterized by a game. So when you have the perfect set property, the appropriate game is determined. So in this extension, we've also shown that a certain game is determined, which is quite interesting. So we have more determinacy than in ZFC. And another result proved in almost the same way is that again, if you collapse an inaccessible to kappa plus, and you have in the extension, you have a function on the kappa Baire space, and the function is definable from a kappa sequence of ordinals, then there is a perfect set, and the restriction of the function to this perfect set is continuous. Okay, this is another result which you get in the same way. Okay. And I want to mention that from maximality principle, you can get a similar conclusion. So what's the maximality principle? I'm not sure. I think it was defined by Joel Hemkins. So we fix a certain class of forcings gamma, and we fix a set of parameters. In this case, let's just say h mu for some cardinal mu. So the maximality principle says that if you have any statement phi with parameters in this parameter set, and suppose this has the property that you can force phi to be true in some extension so that it remains true in all further extensions as well, then it was already true in the ground model. And let's look at since we here work with the Levy collapse, let's look at a certain class of collapse forcings and the associated maximality principle. So we take cardinals nu which are sufficiently closed in this definition. We take the collapse forcings, collapsing these cardinals nu to kappa plus. So then the maximality principle associated for these forcings is consistent. So Gunther Fuchs showed that if you have, so kappa is again a regular cardinal. You have this regular cardinal delta above kappa, so that V delta is elementary in V, and you collapse delta to kappa plus, then this maximality principle holds. Okay, and we can but this principle also implies the perfect set property for, in this case, for the sets which are definable from a subset of kappa. Okay, any questions? So I would like to give a proof sketch of this result. So the problem was the factoring that I mentioned here, and so let's see how we can overcome it. So what we're going to do is we're going to add a tree by forcing. So if you add a cone wheel, you also add a perfect set of cone wheels. So we want to do the same thing here. You can just add perfect tree we add a perfect subtree of 2 to the less than kappa by conditions of size less than kappa. This will, in a similar way, give us a perfect tree of height kappa, so that all the branches to that tree are going to be cone subsets of kappa over the ground model. And in fact, so 2 of them will be mutually generic. And if we do this in the right way, we can control the factors of the forcing. That's what this forcing is going to do. So for notation, L just denotes the length of a sequence. And if you have, that's part 1. It's the length of a sequence of a node in the tree. If we have a set of nodes, for example, this will be a condition. A condition in the forcing gives you a little piece of the tree that we want to force. And the length of that is defined as the super of the length of all its elements. And the forcing conditions are of the form SN3. They're going to be pairs. So we just force with with approximation to this tree. So little t is an approximation to the tree that we want to add by forcing. And so then we have the subset F, S in the condition. And this is going to tell you which nodes are, are not splitting. Right, so S is just determines the set of non-splitting nodes. Okay, so the forcing just adds by approximation a perfect set tree T, a perfect tree T, and the little s is going to give you the set of non-splitting nodes. Okay, so the way this is defined in the forcing is so T is this approximation to the tree that we force, and we want this to be at most binary branching tree. That's condition 3. And we want that for the nodes U and S, any node U and S can have at most one successor, so you cannot split in S. This is condition 4. Okay, it's quite simple way to add such a tree. Any questions? Okay. Also, you can note that this tree is this forcing has size kappa, and it's less than kappa close. Actually, it's equivalent to just adding a cone subset of kappa. Let's see how we can use this forcing. So take the generic filter, and we look at all the first coordinates of the conditions in the generic filter, the little t. So if we union them up, we're going to get this tree. Let's call it TG. And let's take a name T dot for that tree. and this tree generates the generic extension. Okay, and then it's quite easy to show that if you look at two distinct branches in this tree, so each of them is generic for the forcing that adds a cone subset of kappa, and moreover, the pair of them is generic for the product forcing. It's just a calculation. So we've added a perfect tree of mutually generic cone subset of kappa. Okay. Now, how about the factors we want to compute? We want to take some branch in this tree, and we want to calculate the quotient forcing to that. To do this, first, we look in conditions which determine the, let's take a name for a branch. Let's call this B dot. So in the generic extension, we want to take some branch in the tree. So now we take a name B dot for it. And for any condition, we can look at the part of B that is already decided by that condition. So remember, the condition is a tree smaller than kappa with a set of non-splitting nodes in T. And we don't know how much of this branch P decides, but it can only decide the branch up to the height of that tree. That's also quite easy to show. That's this lemma. So you cannot decide if a condition has length. Let's see. So the branch. So this is the part of the B dot that is decided by P. Okay, let's say this has height delta. Then delta can be at most the height of the tree T in this condition here. So that's what this lemma says. If you have a part of the branch that's decided, then this is already in T. So the delta, by this property, the delta can be at most the height of the tree T. Okay. And we want to look at a dense set of conditions, those which decide the branch up to the height of the condition. So we have condition Ts. T has a certain height, and this condition decides the branch up to the height, the same height. And it's easy to see that this is a dense subset of the forcing. This we need to compute the quotient, and I just want to sketch the idea how to compute the quotient. Okay, so again, the situation is we add this perfect tree, we take a branch, and we want to know what is the quotient forcing for that. And to compute that, we modify P a bit, we expand it a little bit, so that we can do this calculation. So this is the forcing Q, which is going to be equivalent to P. So Q is this, just take all the conditions P in this dense set and add, in the first coordinate, add this piece of the branch that is already decided. And you get a forcing that's equivalent to the original forcing P. Okay. I mean, this is ordered, of course, in the second coordinate we order like P. Here we order by reverse inclusion. That's this. And then we're going to have a subforcing of this, which is Q0. And this is just going to add the branch itself. So we want to look at a subforcing which adds the branch, and then we would want to compute the quotient. So let's divide the forcing into this part, which just gives you the branch. And then we have Q1 is just, let's see. Okay, Q1 is the remaining part of Q. Okay. And then, of course, this condition is stronger than this one, so therefore Q1 is going to be dense in Q. And clearly these maps are isomorphisms. So if you look at, so what we did here, we take condition P and D, and we just add this information about the branch. So the map which maps P to this condition is an isomorphism. And also if you look at this forcing is just the same forcing as adding a cone subset of kappa, because it's ordered by inclusion. Okay, so now we already see that the first part of the forcing adds a cone subset of kappa. See? Well, P is equivalent to Q. We just add a little bit of information to every condition. And so we need this lemma here to we want to show that Q0 is a complete subforcing of Q, and it's easy to calculate using this lemma here. That I guess I can skip. Well, okay, why not? So we have this condition, and we have some condition where in Q0, meaning the second coordinate is 1, and this one extends the first condition. Then you can easily see that these two are compatible because you can add the piece of Q, the piece of BQ that is above BP here. You can just add on top of the BQ, and you can see that that is a condition in Q. And that easily shows that Q0 is a complete subforcing. So this shows that the Q0 adds which adds the branch, and this is equivalent to a Cohen subset of kappa. Okay. And now, what about the quotient? Well, the quotient, take any branch, take any generic filter for this forcing, and let's say we have a name for a branch again. Okay, name for a branch means there's a condition forcing, this is a branch in this generic tree. And then the quotient, so the whole forcing Q is equivalent to adding a Cohen subset of kappa, and the subforcing Q0 also adds a Cohen subset of kappa, and this lemma says that the quotient forcing is also equivalent to that. And this we can just calculate from, well, it's a calculation that we can do. Okay, so this is what you need in the proof. So now I can sketch, wanted to sketch the idea of this perfect set property. So this is just the essential step. Once you have this, we can now show the perfect set property, similar to Solovey's proof, same idea. So we have some regular cardinal kappa. We have an inaccessible cardinal lambda above kappa, and we do a Levy collapse. And the claim is then the perfect set property holds for all sets that are definable from kappa sequences of ordinals in that extension. Okay, so here's the argument. Suppose you have a, you have a set, definable set A. So it's defined by a formula phi, and some parameter y, which is a kappa sequence of ordinals. Let's just write A phi for this. So A phi means the set obtained by applying the definition phi with the parameter y. And in this case, we want to apply it in the extension Vg. So let's call the set A here. And we trying to show that this A has the perfect set property here. Okay. So A is just any set definable from a kappa sequence of ordinals. We have two cases. Well, if either kappa is small, well, that's one of the cases. If either A has size at most kappa, and if A has size kappa plus, then we want to construct a perfect subset. So how do we do this? Well, first of all, you can find, well, if in the extension A has size kappa plus, then there have to be more and more elements added when you collapse more and more. Because otherwise the set is small. So there is some mu, so that when you collapse mu in the extension, that already adds you a new element of A. That's what this says. So there is some mu which we can choose to be sufficiently closed here, so that collapsing mu already adds a new element of A. That's clear? Okay, now let's take, so this is the extension with the collapse including mu, so this collapses mu as well. And over this extension, so the quotient to the whole extension is just a collapse, but now we want to first add a Cohen subset of kappa, and then after that to the Levy collapse and see what happens. So why do we do that? Because the thing is, if you add, over this thing you add a Cohen subset of kappa, it's the same as doing another collapse of mu, because the collapse forcing for mu in here has size kappa, and it's less than kappa closed. So what's going on here is just the same as doing a call kappa mu extension again. But in this situation here, we know that if you collapse mu, then you're going to add a new element of A. So the same thing is going to happen here. Yeah, so because of this assumption, this is forced over V, and then this also has to hold in this extension. So we know that, let's see, this should be mu plus, but because of this assumption here, and this is the same type of forcing, in this VG also there is a new element of A. Okay, and also these two are disjoint because they're mutually generic. So what's going on here is that if we have this intermediate extension and we add just the cone subset of kappa, we're going to add a new element of A here. That's all we need, because now over this extension we add this perfect tree, perfect set, and we know that all the elements of this perfect set are cone subsets of kappa. So this is like the G here. We know by this property now that there's a new element of A when you add this cone subset over here. So we have a sigma, named sigma for a new element. So now we add just a perfect tree of these cone subsets of kappa. That's what P does. And afterwards we do the Levy collapse. And now what happens is that in this intermediate extension of G bar, you have this perfect set, and each of these sets gives you an interpretation of sigma, and all of them factor properly, and therefore this is going to be a perfect subset of A. Okay? Any questions about this proof sketch? Let's see. Okay, I would like to move to the superperfect sets. So, I mean, this result begs the question: what happens to the superperfect sets? So there's a well-known classical dichotomy result for the superperfect sets and trees. It was proved by Hurewicz. First for Polish spaces. So he showed that he characterized the Polish spaces which are not K sigma, meaning, so K sigma means that the space is a union of countably many compact sets. And so he characterized those spaces as the Polish spaces which have a closed subset that is homeomorphic to the Baire space. Okay. So if you have the set homeomorphic to the Baire space, then clearly the space is not K sigma, because omega to the omega is not K sigma. And he proved that it's an if and only if, and it's a very short proof. It's a few line proof. And then this was extended in various ways. For example, was proved by Kekris and Saint-Amand that if you take any sigma 1,1 subset of a Polish space X, so the sigma 1,1 set is A. This theorem generalizes. So we want to look at the sets A which do not contain which are not covered by a K sigma set, and these are the properties characterized is equivalent to the property that there is a closed subset of A which is homeomorphic to the Baire space. Okay. So this is like a similar dichotomy as the perfect set property, and I guess there are many more dichotomies that you could look at in this context of kappa to the kappa as well. So Kekris also generalized this to two projective sets. For example, I'm not sure, maybe to using determinacy, maybe to all sets of reals. So the question that we asked in joint work with Philipp Schlicht and Luca Motoros is, we want to generalize this theorem to kappa to the kappa. And so again, it turns out that it's independent. And first we need to see what are the right definitions. So K sigma, K sigma means it's the union of countably many compact sets. So the analog of compact set here is kappa compact. So kappa compact, I think also called kappa Lindelöf, means that if you have any open cover of that set, there is a subcover of size less than kappa. So if kappa is omega, this is just compactness, and it's a direct generalization. And then let's say K kappa for the union of kappa many kappa compact sets. Okay, And a subset of kappa the kappa is said to satisfy the Hurewicz dichotomy if one of two cases holds. Either A is covered by a k-kappa set, or A has a closed subset which is homeomorphic to kappa to the kappa. So the statement is the direct analog of the statement here, this theorem here, right? So in these words, this theorem says all sigma 1,1 subsets of Potus spaces satisfy the Hurewicz dichotomy for omega. So now you can ask what happens for kappa to the kappa. Do all sigma 1,1 subsets of kappa to the kappa satisfy the Hurewicz dichotomy? And there are various ways in which this can be forced. So there's a nice poset which is kappa plus CC and less than kappa closed, which forces this dichotomy. So if you take any regular cardinal kappa, you can force this dichotomy. And moreover, this can be done globally. So there's a class forcing which it's an iteration in which you iterate the forcings used for this step, and you can preserve. Well, we start from a model of GCH and then force this dichotomy at all regular kappa, and you can preserve we preserve cofinalities and several large cardinals. Okay, so this forces the Hurewicz dichotomy. Okay, so then of course there's a question in which models is this dichotomy false. So it's also how do you force it to be false? How do you force the dichotomy to be false? So one way to do this is to add a cone subset of mu. So mu is some cardinal below kappa, which with mu to the less than mu is mu, and we add a cone subset of mu. So after doing this, we add this x, then the Hurewicz dichotomy fails for kappa. So we have kappa and we have the smaller mu, we add a cone subset to mu, and then the dichotomy fails. And the reason is because so the counterexample is just the kappa to the kappa of the ground model in this case. So I might say something about the proof if I have time. And also in V equals L, so in L also the dichotomy fails, and so even for closed sets. Okay, so I will want to say a little bit about some basic steps, how this is proved. So let's say a tree is pruned. So I'm talking about this, let's say, so this result here. How do we force the Hurewicz dichotomy? So I just want to give you a few ideas how this is proved, and the basic properties of these sets. So let's work with pruned trees. So a tree is pruned if above every node there's a cofinal branch through the tree. This is the analog to trees without end nodes. And then, so first there are some quite interesting observations that were made a long time ago about these sets. So suppose you have a weakly compact cardinal, then the space 2 to the kappa is kappa compact. And this is an if and only if. So because if kappa is not weakly compact, then the space is actually homeomorphic to kappa to the kappa. And well, kappa to the kappa is not kappa compact, because if you take any node and you take you split up into kappa many disjoint basic open sets, and this cover you can never refine to a small subcover. So if you have a tree which has one node with kappa many direct successors, then that tree does not give you a kappa compact set. And then, well, the question is, are these exactly the trees that give you a kappa compact set? And that also depends on whether kappa is weakly compact or not. So here's one very nice observation as well that characterizes the trees which give you a kappa compact set. So these trees are exactly the trees that are kappa trees, so all the levels are smaller than kappa, and the tree does not have any kappa R and giant subtrees. It's quite a nice observation. So, I mean, this is easy to prove. For example, well, suppose you have a tree with a kappa Arnjan subtree Y. Is the set not kappa compact because you can take you can take the nodes on the boundary of the tree. See. So say we have this Arnjan tree T here, and you take the boundary of the tree. T. So these are the nodes that are not in T, but everything before is in T. So all initial segments of S are in T, but S itself is not in T. This is the boundary. And if you look at the basic open sets attached here, we have a cover of 2 to the kappa. We have a cover of T with kappa many sets, and they're disjoint, so you cannot refine that. So that's not kappa compact. So these are some quite nice ideas. And then let's see. And this is the compactness is related to the property that you can find a element of kappa to the kappa that bounds the set, meaning it's a function that is pointwise above every element of the set. So if A, for example, if A is contained in a kappa compact set, then A has to be bounded. That's because if you look at for example, the tree for a closed set, the levels have to be small, and then on each level, the supremum of the ordinals appear and gives you the function that bounds. That's part 1. Sorry. And okay, so similarly now, if A is contained in a k kappa set, so we have kappa many kappa compact sets, then for each of these you find this bound, and we can diagonalize against that to find an eventual bound for the whole set. So if A is contained in a k kappa set, then A is eventually bounded by some function. And if this can be reversed if kappa is weakly compact. Okay, so these are some basic properties you need for proving the dichotomy in the extension. Also, for example, about the perfect set property, the following are equivalent. So the perfect set property says, well, can be formulated in various ways. You can ask that there is a perfect subset. You can ask that there is that's equivalent to 1. There's a tree, a perfect tree whose set of branches is contained in the set. You can ask there's a continuous injection from 2 to the kappa into the set. For example, these are all equivalent. This is quite useful. And the analogous property for the superperfect trees is this. So let's say we have, we're looking at the set of branches of a certain tree T. So a kappa Miller tree is a tree that is a superperfect tree. It's the same. So above every node there's a kappa splitting node. And suppose we have a kappa Miller subtree of this given tree T. Then, well, this is always homeomorphic to the kappa because the tree is essentially the same. And if kappa is weakly compact, this holds conversely. So if you have, say, kappa is weakly compact and we have a tree T, and let's say that the set of branches of T contains a closed set which is homeomorphic to the kappa, then we can also construct a superperfect subtree of T. Okay, if kappa is weakly compact. So if kappa is non-weakly compact, this is false because then for T you can put 2 to the kappa, because in that case 2 to the kappa is homeomorphic to the kappa. So then this is false. Okay, let's see. So we can get some consequences for regularity properties. So as I mentioned earlier, there are at least 2 ways to define the regularity properties. So there's the one we used here, and then using that definition, using the superperfect trees and kappa Miller trees that we looked at, let's say that, for example, a set is kappa Miller measurable if you take any kappa Miller tree, you can shrink it to a smaller kappa Miller tree, meaning a superperfect tree, which is either disjoint from the set or which is inside the set. Okay, And you can do the same for any type of trees. So this is the property we look at here. And then it also follows that it's consistent that these properties hold for all sigma 1 sets. This was also proved independently by Yuri and others, I think, Yurikomsky. And also they look at, so as I said, there's this different type of regularity property where instead of these trees here, these are just perfect trees. You look at the trees that are used for the kappa Sachs forcing, so where the set of splitting nodes is closed, and then you get completely different regularity properties. So just to warn you that in that case, the regularity properties, analogous to the one defined here, they just fail for provably for sigma 1 sets. Okay. I was going to say something about the proof. Well, so the proof uses kappa Heckler forcing. It's the analogous as the obvious analog to Heckler forcing for omega. But now we want to add an element of kappa to the kappa which bounds everything in the ground model. So this is well-known forcing, which in the first coordinate is an initial segment of this function that we want to force, and you have this reservoir of elements in the ground model that you have to dominate. Okay, and then you can look at a technical condition, and this is the crucial lemma in the proof that so we want to iterate. Let's see, we want to iterate the Heckler forcing in kappa plus many steps. Okay, so there's a case distinction whether the kappa is weakly compact or not, and you also have to be careful whether after forcing kappa remains weakly compact or not. So the two different things, two different forcings you have to apply, and one of them is the Heckler forcing here, and this is the crucial lemma that allows us to prove that in that iterated forcing you get the Hurewicz dichotomy. Which I guess I'm going to skip. But, well, the result is this, that, so you iterate Heckler forcing in kappa plus many steps. And suppose after doing that, kappa is weakly compact, then the Hurewicz dichotomy is true. Okay? So there are many cases that, well, maybe kappa was weakly compact, and then you do this forcing, it's not weakly compact, or it wasn't weakly compact in the first case, and there's a different forcing that does this, where the idea is you take a set in the ground model, and you make this into a k kappa set in the extension. That's this forcing here. Let me just quickly explain the idea. So we want to build, the forcing is supposed to build a k kappa set, so it's going to build kappa many trees. And let's see. So this coloring is gives you the various trees. So this the value of this function is, tells you which trees we're in, and we have certain trees, and in the end these trees will union up to trees in the generic extension, which are going to the union of those sets of branches of the tree is going to be equal to A, so that A is a k kappa set. So what's going on here is that if kappa is not weakly compact, and we iterate this forcing with length kappa plus, then we can force the Hurewicz dichotomy at kappa. Okay, and then this can be combined somehow with the other forcing, which I now skip, to get the global result. Okay. Okay. So let me just any questions? Okay. Yes.
Do you know which weakly compact cardinals survive the Baire iteration?
I haven't thought about
Or
it.
if it happens at all?
Well, over L they do. So they destroy weak compactness, and you can if I mean kappa could be indestructibly weakly compact, then they preserve. But I guess you're asking about the characterization somehow. Right? Oh, I see. Don't know. Yes, for example, in L, you look at the second one in L. You're always going to destroy the weak compactness. Oh, let's see, at least of the least weakly compact cardinal. See. Anyway, so over L we can also force the Hurewicz dichotomy, and this forcing actually separates the Hurewicz dichotomy from the perfect set property if you force over L. So, so now I want to connect. We talked about the perfect sets and the superperfect sets, and this theorem separates the two properties. Okay, and for the first one, we need an inaccessible. For example, here we don't. Also, if you look at the analog to the Solovay model, again, this dichotomy holds. That's this theorem, and it works by the same technique as before. I guess, so I mentioned that the Hurewicz dichotomy and the perfect set property can fail. So, I mean, here's something about the proof, but I will skip this. But, so what you can do is you can add a cone subset to some cardinal mu below kappa here. And the crucial thing is that, that if you look at any tree in the generic extension, if you look at any perfect tree in that extension, the branches of this tree can never be contained in the ground model. So that's somehow a very interesting question that for omega was answered, I think by Groshek and Slayman, and independent by Wooden, or not sure. So for omega, this is not possible for any forcing. If you so if you force, what's the result? If you force with any forcing, you can. I think you never add a perfect tree on of height omega, so that the set of its branches is completely contained in the ground model. It's a very nice result. And for omega 1, this is not known. This is this question. So can you add this perfect tree which lies in the extension, but its branches are all in the ground model? I see. So anyway, for this forcing, that works. Lemma says that. And now what we can do is we add this subset of mu, and the set which is the counterexample to the Hurewicz dichotomy is just the kappa to the kappa of the ground model. And this lemma tells you that it does not have a perfect subset. That's the one direction. Okay, so you just have to prove the other direction, which I leave out. Yeah, so just stating the same again. If you add, for example, a cone wheel, we destroy the Hurewicz dichotomy everywhere. And in L, there's a counterexample, which I'm going to skip. And so let me just end with two interesting open questions. So the result about perfect sets just talks about all definable sets. Definable meaning definable from a kappa sequence of ordinals. And the result about superperfect sets only talks about sigma 1 sets. And we don't yet know if this can be done for other definable sets. That's the first question. And the second question is, what about, yeah, it's related, so what if we want to get the Hurewicz dichotomy for pi 1 sets? So for omega, I'm not quite sure about the status, because there's a paper by Stern where, in which supposedly it's proved that you force over ZFC and you get the Hurewicz dichotomy for omega, for the Baire space, for all projective sets. But as far as I know, this paper is not, it's not known that the proof works. So the people I've talked to, I think maybe the proof doesn't work. So this seems to be an open question. Just what is, I mean, if you look at the Solovay model, the Hurewicz dichotomy is true. But so if that proof doesn't work, it's open whether the Hurewicz dichotomy can be forced over ZFC without an inaccessible cardinal, even for omega. So then there's the question about the consistency strength. Do you need an inaccessible also for kappa? Okay, thank you.
No questions. I think people are focusing on the wine, which is about. So let us thank the speaker again.